Cool. So I'm really excited to be here. I'm really excited that you all made it here, guys, because I hope that you will, by the end of this talk, see that Kotlin is a very cool language, and that concurrency in Kotlin is very cool. And what's even better about flows is that it is really a cherry on top of another really cool thing, the entire concurrency model in Kotlin. But before we dive into the gory technical details, let's start with the story of Mark and his space exploration, which hopefully is going to be less tragic than that of Tony Stark from Avengers. I hope I haven't spoiled to anyone if you haven't seen the latest Avengers. Definitely do. That's one of my favorite movies. Definitely recommend. So it's the year 2049, and Mark is the captain of Leto 2, the second expedition to Mars. And the first expedition disappeared mysteriously, having launched from Phobos, one of Mars' satellites. So they were pretty close. And no one knows what happened to them. So Mark and his team in Leto 2 were sent to discover what happened to Leto 1 and attempt a second landing on Mars. But Mark has traveled a long way from Earth to Phobos, all the way to Phobos, and nothing has happened. He hasn't seen anything extraordinary. And that's something that actually worries him most, because he's there where Leto 1 was, and he should already have some clues what happened to them, but he has no idea yet. And it's time to launch the engines, attempt the landing, and he's pretty nervous about it because he doesn't know what's going to happen. So he orders to launch the engines and hopes for the best, hopes for no unforeseen complications. And this is the code that is used to launch the engines. So Mark is traveling on board a large carrier equipped with massive engines, and they take quite a while to start. Also, because this is such a complex system, it requires some maintenance, right? We wouldn't like our engines to break in the middle of our journey to Mars, so we've got automatic cleaning system which maintains the entire engine system. And this guy takes a while to start as well. So to save some time, we'll want to start both of these asynchronously at the same time. We'll want to start the engines, and while they are kind of getting ready, we'll also want to start the auto-cleaning system. And this is the code that starts the engines. This is the code that Leto 1 used as well. This is kind of the first attempt, which uses kind of standard completable future from Java, which is used to execute a synchronous function and return the result asynchronously. So what it does is it wraps the entire logic in this completable future and returns an int which represents the maximum speed at which the engines can currently go. And this is the equivalent for starting the auto-cleaning system. But to make things a bit more interesting here, we'll want to simulate a failure in the auto-cleaning system, hence we're throwing an exception here. And this is the main driver that launches both of these asynchronous tasks and does the rest, right? So what we do here is we start the asynchronous computation, print a log that we are getting ready to take off, and when the engines are ready, we're going to set off with a maximum speed as reported by the engines, and we're going to report the result of the auto-cleaning system. And from the first sight, that kind of looks all right, right? That looks more or less okay. Let's see what happens when we run this guy. So first of all, we can see that it is indeed run asynchronously because the logs are printed out of order. I had to run it multiple times to get this proper screenshot here. And then the engines are ready, so we do set off. But what we did not notice was that there is a failure in the auto-cleaning system. There is a fire in this system, and we want to do something, we want to extinguish the fire, but it's too late. We're already setting off, pumping more air into the entire engine system, and that might lead to a tragedy. So we've got a possible cause of what happened to Liter 1. And let's see if we can help Mark not get blown up, and let's see if we can help him complete the Mars mission. So one solution to this problem is using combinators, right? What does it help us with? Well, the problem in the previous implementation was that we had two completely separate futures, right? They weren't aware of one another. So when one failed, the second guy was not aware of what was happening, right? So two bad things could happen there, right? If one feature runs and the second one fails, then we leak the reference to the first one, right? We exceptionally exit the main method. If we go back to this example, we exit the entire method and we lose the reference to the first future. And this is a problem because futures are known as hot sources. They are kind of like resources. You need to manage them carefully. You need to open them, you need to do whatever you want with them, and then you need to clean up afterwards. You need to close. And if we complete exceptionally with a second future here, we can't clean up. And then the second bad thing may happen. If the second future fails, and then the first future fails later as well, then we've already lost reference to it, so we have no way of handling the failure of the first future, right? So this is quite bad, and that's what leads to this complications of our space exploration. One possible solution is using combinators, right? As the name suggests, they allow you to combine futures and asynchronous tasks together. Now they are aware of one another, right? We kind of chain these together, and that is more or less fine, actually, right? If we run this code now, we see the logs being printed from starting the futures, then the second future fails, the auto-cleaning system fails, and the cancellation, the failure is propagated back to the first future, and we don't set off. We don't pump more air into our engine system just to explode. So that is more or less fine in theory, except that if you look at this code, well, for me, this is not a piece of code that I would be proud of, right? I mean, I think that calling this spaghetti code is a compliment to this code, right? What we want to do is set off, right? It does take quite a bit of effort to find this set off piece of code, right? It is embedded somewhere deep in the middle, and you don't really know what's happening, right? We had to rewrite a program entirely, right? When you looked at the first example, you knew what was happening, right? You could almost read it sequentially. And now, this is it looks like a completely different program, right? I hope that there are no people here who do write in combinators, because I know that the deeper you go, the less painful it feels. But for me and for other people who don't use it on a daily basis, this is pretty painful. So let's see if there are any alternatives. What we might use is Kotlin coroutines, Kotlin concurrency model. And let's see how that's going to help us, how that's going to help Mark not get blown up, and more importantly, how it's going to help you write asynchronous programs that read very nicely. So first of all, we need to rewrite the asynchronous functions that start the engines and start the auto-cleaning system. So we're not going to wrap it into anything. They're just these functions will simply return their values. The only thing is that they will be suspendable functions, right? We'll add this suspend keyword here, right? And what does suspendable function mean? Suspendable function is a very nice concept in Kotlin, which basically allows you to pause the execution of your program, of your function, without blocking the calling thread, and resume at a later time when you're ready to resume, right? So we're gonna leverage this concept here, and we're gonna rewrite the second function as well. So how does it work, right? This is a pretty good question, right? It sounds like, sounds a bit magical. So what happens under the bonnet is that this suspend keyword, suspendable functions, are actually compiled into functions which implicitly take a callback parameter, right? So if anyone is familiar with JavaScript, there you've got lots of callbacks. So the thing is that you don't need to manage these callbacks yourself, right? This callback is provided there to be called when the execution can be resumed. So no magic anymore, especially that this continuation interface is really, really simple, right? All you have is a coroutine context, which we're gonna talk about in a minute as well. And you've got this function resume with result, right? So you can either resume with your actual result, whatever you have computed, or you can resume with a failure. So you're going to rewrite the second autoclean function as well, not to return any completable futures, but simply to return the values as a suspendable function. But what we also need to do is not only say this function is suspendable, that doesn't do anything. I mean, Kotlin is not that magical. We actually have to make this function suspendable. And what does it is this with context block on your second line. And what it does is it calls the block provided, right, in your curly braces. It calls the block provided, and it pauses and waits until the result is available. And this with context block takes an implicit parameter which you can specify as a dispatcher. So if anyone is familiar with Rx Java, you can here provide your own dispatcher for the exact kind of computation, if you know what you'll be doing. So here we're providing an IO dispatcher, which is ideal if you're just waiting for something, if you know that this is not like computation-heavy operation. So let's see how this allows us to write our main driver function here now. So we've almost gone back to our initial attempt, right? This again reads sequentially, which is perfect, right? I can see what's happening. I can see that I'm calling two asynchronous functions, then I'm printing a log, and then I'm setting off when the result is ready, and then I'm reporting the result here as well. So that's good news. And well, let's just see what is this kind of sprinkle of magic that we've added here. So first of all, we've got this coroutine scope, right, on the first line, which wraps all the functions that we're calling. And not going too deep in here, this is part of the concurrency model that makes it really cool, because what coroutine scope does is it ensures that your concurrency is explicit. The idea is that all your concurrent and parallel computation will be run in some context, right? The idea is that rarely will you actually need to run something concurrently for the entire lifetime of your program, right? You usually want to do something concurrently, get the result, and then go back to your execution. Hence the idea of context. You provide these well-scoped context which know how to handle failure and cancellation. So this propagating failure and cancellation is what we're after. That's the very nice property that allows us to write a program sequentially, and the first asynchronous call will be notified if the second one fails. And the second important property is that this block will not finish until all its children have finished, right? And these two properties really allow us to reason about these parallel constructs almost sequentially, right? Cool. And what else have we got? Well, I mentioned coroutines, right? Where are they and how do we create them? What are they? Well, I had a nice highlight on the slides, but unfortunately I'm not presenting from my laptop, so the highlights have gone. But it is the second and third line. It's just this async wrapper. Well, it's super easy to create. Well, kind of, very minimalistic, if you like, which goes very well with the explanation of what they are. Because coroutines are, well, you can think of them as lightweight threads. So lightweight that you are not only not discouraged to create many of them, but you're actually encouraged to create many of them to be able to structure your concurrent and parallel code in a clean and readable way, right? So that's basically how you create them. You just wrap whatever computation you like in the async block, and that's your coroutine. And in order to run it, you need to make sure that you run it in a coroutine scope, which we have just provided on the first line. And that's it. Off you go. You've got your async, which returns, instead of completable future, we've renamed the variables to engine deferred and cleaning deferred. And deferred is the kind of Java completable future equivalent, except that better because it actually works, right? Just like many things that you take from Java and actually make it work, right? That's quite nice. And in order for our parallel computation, we need all these kind of called scoping functions with context and coroutine scope and async, all these modifiers that we've seen, they all create their own coroutine scope so that you can manage the cancellation and failure in the proper scope, just in the smallest one possible, right? So you actually want your concurrency to be properly structured and split. Cool. So I guess we've helped Mark not get blown up. We found a standard way how to decompose asynchronous computation and how to write it in a nice, readable, almost sequential manner. And now Mark is off from Phobos to finally attempt the landing on Mars. But you should know that Mark is a sensible guy, so, having flown quite a way from Earth to Phobos, Mars satellite, he's not going to just happily jump off and try and land on Mars. Before he does so, he wants to go for a reconnaissance flight, right? So he'll fly around the planet and take a bunch of measurements. He's going to, kind of measure the atmosphere and basically make sure that no one from NASA screwed up and that, say, no measurement, taking software written in Java and just reporting rubbish. So he's going to check it himself, right? He's going to fly around the planet and kind of go into the atmosphere and see what the conditions are like, and basically verify himself if his spaceship is ready to meet the conditions and attempt a landing, right? It'll be quite sad if just attempting to enter the atmosphere, it'll burn like a piece of paper. So he doesn't want that. So there will be a lot of sensors attached to the spaceship. I just have 2, but imagine there are more, right? I mean, 2 is not that many, but imagine there are more. And they will report some kind of process data. And getting these measurements does take a while, so we simulate this by adding a sleep. And then we'll want to return all these to Mark for him to go through all these measurements one by one and verify manually, right? He wants to be really sure, so he wants to verify them manually. He doesn't trust any kind of automated verification here. So that's what he's going to do. He's going to get the measurements and validate them. What you should also know, though, is that there is quite a lot of debris around Mars, right? There are quite a lot of rocks. There is quite a lot of NASA rubbish, like old satellites and stuff like that. So you can't just set a route. You can't just set the autopilot and hope that nothing is going to happen, because you need to actively correct your path. You need to avoid all these obstacles, not to crush into any of these. That would be a bit of a failure as well, right? Being super cautious not to land on Mars without knowing the conditions, and then actually just fly into a rock while taking the measurements, right? That would be a bit ironic. So we've got this active path correction that runs in kind of second thread, if you like, second coroutine, right? So we create a coroutine here with a launch modifier, which is going to just print that we are actively correcting the path, right? Imagine this is the path correction logic, and because this is a coroutine and it's going to start running immediately, then we want to wait for a bit for this guy to launch before we see what's happening there next. So what we're going to do next is we're going to start taking the measurements, right? So we're going to ask for all the readings, which is a collection, and then Mark is going to go through this collection one by one. And again, he needs some time to think it through whether this result is fine or not, so we'll simulate it with a sleep. Cool. And let's see what happens when we run it. So we've got this active correcting path, and it stopped, right? When we're taking the readings, there was no active path correction, right? We have blocked the main thread. So while we are taking the measurements, the spaceship is happily flying into any of the debris that might be around, right? So that is not cool. That is not cool at all. We don't want to fly into these rocks. So that's the first thing that's wrong with this piece of code. And another thing is that Mark said that he wants to verify the results one by one as they're coming in. And that's not what we did. We waited for all the results to be available in the eager collection. We had to have all the results before we created the collection, and then we said to Mark, there you go, all of the results are ready, right? That's not what we wanted to do. We wanted to validate them one by one. So let's see if we can, again, help Mark here to complete his mission. So first of all, what we're going to go back to is our suspendable functions, again, right? we're going to declare the measurement taking functions as suspendable. And then we're going to return all these readings, not in an eager collection, which waits for all the values to be there to be calculated before it can be created, but we're going to return the values in a flow, which is known as a cold collection, right? Cold resource. We don't need to, first of all, manage anything, and we don't need to actually have anything available before we can do something with it. So let's see how we're going to use this flow in our driver code. So we've got the path correction logic unchanged. And then, again, we ask for the readings. Then we'll print them, print the flow. And that's a very quick experiment. We're going to see what happens when we print the flow. And then iterating through this is done using a collect operator on the flow, which is called a terminal operator. And only this operator triggers the execution of the flow, right? Without this collect terminal operator, nothing actually happens with the flow. There is no calculation, right? So you can think of flows as being lazy, if you like, as well, because no computation will be triggered unless you actually finally need it. So again, he's going to look through it and print them. So let's see what happens when we run it. So first of all, we can see that correcting path happens right in the background, kind of in the second thread, just like we wanted. Second of all, when we print the flow right after we have created it, there is nothing to print, right? It's not like with the eager collection when we could print all the elements. All we have is a memory reference, right? This is just an object, a reference to an object, and that's all that we can print. And the collect operator indeed allows us to process the values one by one as they come in, hence without blocking the calling thread. Hence we've got our active path correction and the items printed as they come in. So why are we so excited by this? Isn't this just Kotlin implementation of Rx Java? Why does it matter at all? Why? Well, because it does make a ton of a difference, a whole world of a difference, if you're out there in the space, and Houston is quite far, right? And if something breaks, first of all, or if you actually need to add something to your toolbox yourself, that is super difficult with Rx Java, right? You are not advised to write your own operators. You're not advised to touch it at all. You are given a bunch of operators, a bunch of functions, whatever you like, but if they don't suit you, you're out of luck, pretty much, right? You can't write your own operators which are aware of your business logic, for example, right? Flows follow, just like the entire Kotlin language, the kind of extensible oriented design, if you like. So they do allow users, developers, to extend these features very easily. And in order to do this, they follow very simple design. So what Flows is built of really is, well, the entire thing about Flow really is something, it's an interface that can be collected, right? It's got this really, at its core, a single function which is called collect, and not surprisingly, it's a suspendable function. And it takes a collector. And what is a collector? Well, that is slightly confusing. You might imagine that it's something that it collects something. Well, it doesn't. It's something that emits an item, right? So I like to think of it as emitting an item as declaring as being available later, right? When you trigger the flow and when you actually want to do something with it. And we're also, at the very core, provided like a default implementation of collect with a default instance of flow collector, right, which overrides the submit function. And what does it do at the very end? Well, at the top of the collect function, you provide an action, right, something that you want to do with each of the items. And somewhere deep down, all we do is we call this action method on each of the values, right? Pretty simple. And what this allows us to do, this very simple extensible design, is it allows us to write our own operators, right? We are actually given a transform operator which is explicitly said that it should be used to write your own operators, right? Which is very nice. So we can just take this guy and we are given access to each of the elements. We are given access to the sensor reading because we said that we want to write a validate measurement function which is going to operate specifically on the flow of a sensor reading, right? So this is a business-aware operator, business logic-aware operator. And, you know, we do some kind of validation logic, doesn't really matter. And when you use it, you don't see a difference between the built-in operator and your own custom operator, which is quite nice. For an acute observer, you might notice another very important thing. There are no subscriptions. If anyone is familiar with RxJava, you know that you do get a subscription object, and you should be very, very careful managing it, because if you're not, you risk leaking resources again. There is no such thing in flows. You just create your flow, right? And whenever you attach some kind of intermediate operators, you are operating on the flow all the time, right? And the only thing at the very end that you can do is call collect. And when you do call collect, then you evaluate whatever is in the flow one by one, and then it's gone, right? No reference. You've got unit type, right? Which is, you know, nothing left, like void in Java, right? So nothing to manage. Very nice again. Not surprisingly, you can write your own error handlers, right? So you don't need to juggle exceptions. You can write your own, again, error handler, which is aware of your business logic, right? So you can have specific behavior. You can have behavior specific to your domain. And what is pretty important for like Android developers, or like, well, for kind of tuning your execution, is that you can change the execution context, right? You can use the dispatcher again. If upstream you've got lots of kind of I/O operations, you can switch your dispatcher for a bit, do the I/O heavy computation, and then go back to your default dispatcher, or to switch to CPU dispatcher. And this is kind of still, just that part of it has been stabilized, so it is still being kind of actively developed. And as a proof of this, we've got a new operator coming in, which is called merge. Not surprisingly, it merges to flows. This is one of basic things that was still missing in there. So you can now merge your flows and you know, operate on merge flows. What is still missing, though, and it's pretty annoying because we have been talking about all these parallel and concurrent operations, is that you can't process your flow concurrently, which is a bit of a bummer, right? Because you've got this nice called flow, and you might think that you'd like to go, like, you know, split your computation on the various items. You can't do that just yet, unfortunately. There are a few suggestions on how to do it. This is one of these. I think this is a bit unfortunate because it kind of loses the nice readability of Kotlin and flows and the entire nice concurrency model, because what you need to do here is, you've got this nice operator which says concurrent of 4, right? We want to do it in 4 threads, for example. And then you say what you want to do at the end, what's going to be the terminal collect operator. But this collect is actually given inside this concurrent operator, which means that this is not like a proper collect, that your flow would not be triggered unless you add another collect. And this kind of, just kind of starts to look very magical, right? It's not kind of obvious anymore. So thanks for your attention, guys. I hope you enjoyed it. If you would like to mess around with the code, it is available up on GitHub, and so is the presentation on GitHub pages. Feel free to catch me either at a conference or drop me a line on LinkedIn or in GitHub. And I was just asked to give a very quick shameless plug at the end to my sponsor, Codete. So if I don't think they've got any Haskell openings, but they've got a few Scala openings. So do visit the website codete/carrier. Thanks.
Thank you. We have time for questions.
Yep.
Hi. Are you familiar yourself with modern Scala development, like the cats and Zio and all the type effect system modern ones?
If by familiar you mean I went to a conference which was full of Zio, then yes. If by familiar you mean I have used it, then no.
So yeah, I think it's good. So my question is, how does this coroutine things compares to like cat's effect, let's say? How can you compare them in terms of performance and ease of use and expressiveness?
Right. So I think that relates more to being familiar myself, using it. So having not used it, I can't really compare the performance, first of all. Second of all, off the top of my head, I think they are slightly different concepts because coroutines are really kind of like a nice alternative to threads, if you like. And as far as I'm aware, cats is kind of like a more, kind of functional approach, a slightly different, slightly broader concept, right? So I'm not super familiar with cat, so it's a bit hard for me to compare. But is cats like an alternative to threads?
No, I mean cats effect, not the cats per se, but
okay.
Cats effect library. So they provide an effect type, which has like sort of coroutine types, and so it's I think it's basically the same. So in terms of usage, but well, I was thinking maybe there is some kind of peculiarity. So okay, yeah, thank you.
Yeah,
thank you
sorry, I'm not a cat effect user really. Any other questions?
Looks like there is no more questions. So
Sweet.
Thank you
Coffee
again,
time.
Krystian.
Thank you.